I would like to go over 3 first-year linear algebra questions that are more proof-based rather than computations. It involves matrices and matrix invertibility and all that kind of stuff, matrix multiplication. So should familiarize with the rules first, but if you do know all the rules, then I'll just start going over these 3 implication questions. Okay, they're not too hard to prove, so they're pretty fun to do as well. So for the first one, we have the antecedent, or the assumption, with 2 premises that a squared is equal to a, where a is some matrix, and that ax is equal to y, where x and y are column vectors. Then the conclusion is ay is equal to y. Okay, and by the way, this operator here is the logical operator conjunction, and okay, it's the logical conjunction operator. It's just and. Okay. Anywho, if we start off with the premise that we know, let's say we start off with ax is equal to y. If we start off with this, then we can multiply both sides of the equation by the matrix A again. And for matrices, you should multiply the matrix on either the right side or the left side on both sides. What I mean is, here I multiplied A on the left side of the expression ax, so I should multiply A on the left side of the expression y. Okay, and if I multiply, let's say, A on the right side of the expression, then I'll have to multiply A on the right side of the expression on the other side. Okay, so this is what we have. What is A times A though? Okay, A times A we know is A squared. So we have A squared times x is equal to A times y. All right, so this implies that, well, what's A squared? Well, from the other premise, we know A squared is equal to A. So A times x, that is equal to ay. Okay, so this implies, well, we know what ax is equal to. From the very beginning, we say ax was equal to y. So therefore, y is equal to ay. And because it doesn't matter which side you're on for the equality symbol, if y is equal to ay is equal to y. That's just what equality means. Okay, the left and right side are the same. Anywho, therefore, I'm just going to say implication holds. Okay, now generally when I do a question like this, what I will do is I will probably just say if ax is equal to y, then we have ax is equal to ay, which equals to, and then I start from here. So ax is a squared x, and a squared is a from one of the premises. So a squared is ax. Well, ax is equal to y. So then we have this chain of equalities, equal signs. So then what we have is y is equal to ay. Okay, so in the end, from here, you just boil down that ay is equal to y. Or you don't. I don't know. I just think that I personally would just write equal signs, but because this is all equality. Though, however, I think it is good to show implication signs like that, step by step, just to show you how each step came from the previous one. Okay, so that's just the first part. Next, we have, given that A minus B is invertible, where A and B are square matrices, so their difference is also a square matrix, and only square matrices are invertible. Not every square matrix is invertible, but in order for a matrix to be invertible, it has to be square. Okay, so A minus B, they're both square matrices of dimension, let's say n. Their difference is also square, it's invertible, and we have a non-zero column vector, y, and then we have A times V is equal to y, and B times W is equal to y for some column vectors V and W. So we're saying that there exists solutions V and W such that the matrix A times V gives you y, and the matrix B times W gives you y. Then we need to conclude that the V and W, they're not equal to each other, okay? To do this question, I recommend using proof by contradiction. So let's suppose we have our premise, our assumption right here, the antecedent. Suppose all of this is true. These are our premises. And let's add how many premises do we have? We have 1, 2, 3, 4. Okay, so suppose we add a fifth one. Okay, and the fifth one is going to be that V is equal to W. Okay, so suppose this is true. Okay, so we add this hypothesis, and you're going to see that it's going to conflict with one of the premises in our assumption, or the antecedent. Okay, so suppose V is equal to W. Then what you have is that, well, if V is equal to W, okay, no problem. Then we have AV is, well, actually, I'll just end it off like that. Okay, so now let's start with AV is equaling to BW, okay, because they're both equal to Y, right? Y is equal to AV is equal to BW, okay, is equal to Y. I'm just gonna write that down. Then what does this mean? This means that if we move the BW to the other side, we have AV minus BW. That is going to give you the zero vector, the zero column vector, because AV is a column vector and B times W is going to be a column vector. Okay, so their difference is zero, so it's the zero column vector. So right here we see that we can actually factor out because V is equal to W right here, I'm gonna replace this W with V. Okay, so we have AV minus BW, but W is V from this hypothesis. This is what we're assuming. We don't know if this is the right assumption, given that these assumptions are what we have, okay, are the antecedents that we have. This one I just added in for the sake of, let's say, testing, okay, but the ones, the antecedents, the premises and the antecedent that were given to us are for sure we're assuming to be true, but for this V is equal to W, this is just our own little hypothesis. So we have BW, okay, is the same thing as BV. Okay, so we can see here that we can factor out the V. So we have V multiplied by A minus B, or you can say A minus B times V. It actually does matter. Oops, I should probably do this right here. I should probably do a minus b times v. Because of the nature of the matrix, let's say a minus b is an n by n matrix, and v is a column vector, so it's going to be n by 1 column vector, so it's going to equal 0, a 0 column vector. Inner dimensions have to be the same. If I did it the other way, v times a minus b, v is a column vector, and a minus b is a square matrix. So if this is n times n by 1, this is n by n, then I can't multiply it. Right? You cannot multiply something like that. But unless I change the v, if I transpose it to become a row vector times a square matrix, that is doable. Okay, because we'll be left with a 1 by n and n by n. But the resulting is going to be a resulting result is going to be a 1 by 1. Oh, sorry, this is n by n. 1 by n. Row vector, row matrix. Blah. Cannot speak today. It's been a while since I made these videos. Bear with me. Anywho, so we have this. Okay, so notice that we have a minus b times the column vector v. That gives you the 0 column vector. So what we have here? So this implies that, well, either a minus b is the 0 matrix or v is the 0 column vector. Okay, so let's see here. Is it possible for a minus b to be the 0 matrix? Well, recall a minus b is invertible. So a minus b is invertible. It is not the case that a minus b is the square matrix. Okay, because what matrix do you multiply with the square matrix to give you the identity, right? It's like, what number do you multiply 0 by to give you 1, right? Nothing. Okay, a minus b, if it's invertible, that means it cannot be the 0 matrix. So we have that a minus b cannot be the 0 matrix. That means v is the square. V is the 0 column vector. That means v is the 0 column vector, right? That makes sense, right? A square matrix times the 0 column vector gives you back the 0 column vector. Okay. So if v is equal to 0, that means w is also equal to 0. Then what we have here is that if this is true, then if we go back to this AV and BW, then we have AV is equal to BW, which equals to, so AV, which equals to BW, which equals to V is what? V is 0, and W is the 0 vector. But A times 0, B times 0, that gives you 0. But we're saying, which equals to Y, right? Which equals to 0. Uh-oh. That's not good. Because we said that, or not we, but the question stated that Y is non-zero. Okay, Y is a non-zero column vector. When we supposed V was equal to W, it contradicts one of the premises in our antecedent. Okay, these are the premises that hold, or are what we're taking in to be true. Okay, so these are what we're taking in to be true. This assumption V is equal to W was something we added in later on. It was like a hypothesis. And we're trying to see is that given our antecedent is true, all of these four premises are true, can I add V is equaling to W without its result contradicting any of our four premises? And we see that it is no good, because when we suppose V is equal to W, we get a result that y was the 0 column vector, and this lightning bolt is the contradiction symbol. There are other symbols as well, but I prefer the lightning bolt. This y is equal to 0 contradicts our premise right here. Y cannot be the 0 column vector. So that is no good. So therefore, by contradiction, proof of contradiction, this assumption was false. Okay, this v equaling to w was not good. Okay, so we have v cannot equal w, because if it did equal to w, then we get a result that conflicts with a result we already said or we're taking it to be true. Okay, so given that these 4 premises are true, this has to be the conclusion. V cannot equal to w, because if v did equal to w and these 4 premises are true, so we have these 5 premises, then we get a contradiction. Then we get something false. So this statement right here is true, because if we suppose the negation, if we have logic, if we have P implies Q, if this whole thing is true, then what's the negation of P implies Q? Statement P implies statement Q. The negation of it is statement P and not Q. So that's the symbol for not, or not Q. Then this has to be false. Okay, if there is rain, then there is cloud. Okay, that's true. If there is rain, then there is cloud. But if we say if there is rain and no clouds, then that's false. But I'm getting off tangent over here. This logical operator stuff excites me. Symbolic logic is fun. Anywho, this is basically what you do. Sorry that it's taking too long, but you can always fast forward the videos. Okay, so but then again, I should probably be more concise and succinct in what I'm trying to say. Okay, so the last question, we have the square matrix A minus I, the identity. Okay, let's say they're both dimension n. A minus I whole thing squared, if that equals to the 0 matrix, then we have to say that A inverse exists. So given that A minus I squared gives you 0, show that its inverse exists, and I should probably add that you can write in A inverse explicitly. Okay, so what can we do here? So we have this antecedent. Suppose, or not suppose, well, yeah, okay, suppose A minus I squared is equal to 0. This is not my hypothesis right over here for proof of contradiction. This is just, okay, a statement that this is true. Okay, given A minus I whole thing squared is equal to 0, okay, suppose this is true, then what can we conclude? Then we conclude that, well, just expand out the fraction. I'm going to say this is equal to, well, A minus I squared. Well, that's just A minus I times A minus I. That equals to, you can FOIL this out, distribute A squared minus AI minus IA plus I squared. And by the way, AI is equal to IA, because identity matrix times any matrix is just itself. So it doesn't matter if you're doing it on the right-hand side or the left-hand side. Okay, so I'm just gonna say this is A squared minus AI is equal to IA, so I'm just gonna say this is 2 IAs. Okay, or you can say 2 AIs, it doesn't matter. Okay. I'll just do 2 AI plus I, well, I squared is just I, right? I times I is just, well, if I replace A with I here, then I get I. It's like 1 squared is equal to 1. Okay, identity times itself is I, okay? And we get that this is equal to 0. And this is good because we have the identity matrix by itself here, okay? So we can imply that if we move, remember this whole expression is equal to the 0 matrix here. If we move the a squared minus 2ai over to the other side, we get I is equal to positive 2ai minus a squared, which equals to, if I factor out the a, then I get a times 2i minus a. Okay, this is good. And by the way, I could write it like this, is equal to 2a minus a squared. It's just that when you write it like this and you try to factor out the a, you're tempted to probably do a times 2 minus a squared. Oops, 2 minus a. And treat it like variables. However, we should know that a is a matrix, okay? It's not a number, okay? It's not like a column vector or something like that. It's a matrix that, well, I wouldn't say column. Even if it's a column vector, this wouldn't be good as well, because this 2 right here is a real number. 2 belongs in R1. Okay, it's just a real number. But if we have like a multi-dimensional vector, if you have a matrix, then that's not good. Okay, because the number 2, you cannot subtract a matrix, a square matrix, away from a number 2. I guess unless you say that this matrix A is somehow 1 by 1. Okay, if we say 2 minus 1, then I get 1, but that's just weird notation. But I just, whenever you factor out this A right here, just to remember to put the identity matrix back, because if the A was a square matrix that was 2 dimensions or more, 2 by 2, 3 by 3, then you kind of need this I. Okay, but that is just a side note. But what can we conclude right here? We conclude that A times whatever this matrix is gives you the identity, okay? And that's exactly what the inverse means, okay? A times A inverse gives you the identity, okay? Which equals to A inverse times A. So here we have A multiplied by this other matrix, 2i minus A. That gives you the identity, okay? Then we can imply that A inverse is equal to 2i minus A, which implies A inverse exists. Therefore, implication holds. And that is it. Should finish something off here. Therefore, implication holds. And that is it. Okay, so hopefully you found these 3 problems interesting. And if there is anything I said that didn't make sense, please let me know. I am still trying my best to explain these problems out, and occasionally I may have used some words that are inappropriate here or there. But in general, this is how you'll do it. Okay, thank you very much for watching and listening to me going off tangents and on spiels.